Welcome everyone to this podcast. My name is Prof Muaaz Bhamjee, and I'm an associate professor in the Department of Mechanical and Aeronautical Engineering in the Faculty of Engineering, Built Environment and Information Technology at the University of Pretoria. I'm going to be talking to you about my research, which to me is absolutely fascinating. I'm not sure if everyone agrees with me, but I make them agree with me. So what do? I would argue that I do something very broad, which is computational science. What is computational science? So there are a lot of problems that have to leverage very specific mathematical techniques and coding to actually solve those problems. The particular one that I am most involved in is computational fluid dynamics. What is computational fluid dynamics? Computational fluid dynamics is a field that leverages unique mathematical techniques such as numerical methods to approximate the solutions to the equations that govern the way fluids behave. What does that mean? It means that the equations for fluid dynamics, at least to us currently, is analytically unsolvable for the general case, which means for complex geometries with complex boundary conditions or complex physics, and sometimes coupled physics such as heat and mass transfer or a coupled electromagnetic field, we cannot solve those equations to find what is called a smooth solution or a closed form solution. So to do that, we need to use uh, very specific mathematical techniques to approximate solutions within a certain numerical error. And to do that, we leverage large-scale computers and code. And that is the field that I work in. But that field has been growing recently. And one of the areas it's been growing into recently is artificial intelligence, specifically scientific AI. Now you're thinking, what does ChatGPT or Gemini have to do with this? Well, something and nothing. AI is a very broad field that encompasses, for example, large language models, which is a subset of natural language processing. What does that mean? It means that ChatGPT, Gemini, etc., yes, it's an important area of AI, but it's not the only part. It's an area that falls under large language models and to a larger extent, natural language processing. The area that I work in is scientific AI. Now, scientific AI utilizes the fundamentals of what we call a neural network, which is a model of how our brain works. And we mathematically model the structure with certain assumptions, and we use that to train this model on a lot of data to pick up what we called a feature mapping. What is a feature mapping? So we actually give it the inputs, and we also tell it what is the solution. And by doing that, it learns the correlation between the inputs and the outputs. So it actually creates a function or mathematical relationship to relate the inputs and the outputs. And that can be leveraged to solve really complex problems. For example, we can use it, we can use a subset of neural networks such as convolutional neural networks to do image processing, such as pattern recognition. For example, how does your phone actually realize when it takes a photo what is your face or what is a dog in the photo? It uses something like convolutional neural networks or derivatives thereof to analyze that and do classification algorithms or semantic segmentation. Those are just the fancy words for deciding in classification whether an object is a dog, a cat, or a ball. And semantic segmentation is to actually analyze more than one object within an image. Now, convolutional neural networks are not new. They were devised many decades ago by researchers, and these are really important techniques. And as you can see, they go outside of the sphere of ChatGPT and Gemini or large language models. We can train machines or these machine learning algorithms to recognize these feature mappings in problems such as computational fluid dynamics or in, for example, biology or chemistry, etc. Techniques that we often use could be, for example, graph neural networks, which is another subset of neural networks or machine learning, or we can use what's called generative adversarial neural networks to do what we call super resolution. That, for example, is a really interesting one. The problem is if we want to solve it really fine and we want to extract a lot of the nuance in the simulation and the small scale features in the physics, we would solve that problem on a lot of CPU or graphics processing units, but that eats up a lot of compute time. The solutions are slow. So we can actually we can train a large data set of coarser simulation results as well as the more detailed simulation results. And then we can train a model on the mapping between the coarse and the finer solutions. And then from there, we do what's called inferencing, where we feed it unseen data, and then it actually generates, or the unseen data would be coarser simulations, and then it would generate from what it's learned about that feature mapping, it would generate a solution on a finer grid. And these are the interesting things we can do to accelerate these solutions so that we can use less compute and generate solutions faster. But one of the key things to do is to ensure that we still keep the accuracy there and we preserve the physics of the problem. And that's an active area right now, and is actually one of the areas that I and my postgraduate students are actively working on, is how do we keep the benefit of speed from such methods without compromising the accuracy of those solutions. And then we are now also looking to the next frontier of computing, which for me is really the most exciting, which is quantum computing. And quantum computing leverages the principles of quantum mechanics to accelerate our compute capabilities. But it's wholly different from the computer that we see today. And there are quantum computers around that we can utilize. And there are still challenges around quantum computing, but it is still seen as the next frontier of computing. So within my research group, what are we working on? We're working on, for example, how do we port or to move these quantum or these computational fluid dynamics codes from your classical compute architecture, which is the computers you currently used to, onto these quantum computers. And that is a really interesting avenue. It's a challenging research area, but it's a research area with immense promise. And if we can succeed, we can again reduce the time it takes to generate these solutions and to make meaningful impact on society. And now the question you might be asking, this is a lot of science, fluid dynamics, computing, code, software, computing hardware, etc. What does this mean for the average person? Well, let me take you to what computational fluid dynamics impacts. Computational fluid dynamics is used to analyze the aerodynamics in your car. It's used to analyze the aerodynamics or the combustion behavior in your car. It analyzes similar in airplanes, helicopters. It's used to analyze the aerodynamics in drones. It's also used in the medical field to analyze different medical devices where fluids are prevalent, for example, in ventricular peritoneal shunts. We also use it to analyze blood flow in specific conditions. A really great piece of work that one of my master's students recently completed was looking at modeling aeroacoustics in lungs for different pathologies, for example, in tuberculosis, pneumonia, as well as cavitary tuberculosis, as well as bronchiectasis versus in healthy lungs. And he was able to recover the sound signatures for those specific conditions and to map that against the anonymized audio recordings of patients with similar pathologies. Why is that important? By showing that computational fluid dynamics can accurately recover those sound signals, he now premises that we can actually generate synthetic data to train an artificial intelligence or machine learning algorithm to later do telemedicine, not to replace doctors, but to assist doctors in doing remote diagnosis for patients who live in remote areas and have limited access to specialist care, but need very fast diagnosis. And then we can do a clinical diagnosis and triage. Now, I've had the privilege of utilizing computational fluid dynamics, AI, and quantum computing for many different interesting projects, ones that have real impact on society as well as on science. So I gave you a really great example of how it can impact society by using it for medical applications. Now I'm going to take you to how we impact science. For example, I work on the ATLAS experiment at CERN. What is CERN? CERN is the place where the largest high energy physics experiment is housed. What do we do there? We try to understand the fundamental building blocks of nature. We analyze particle behavior or particle physics. For example, CERN is most renowned for being the place where we discovered the Higgs boson. But we continue at research. We continue to find the frontiers of what we call now beyond standard model physics. What does this have to do with engineering? Well, everything. The Large Hadron Collider is an absolute marvel of engineering excellence. And South African engineers are playing a pivotal role in that area. Myself, my research group, and my collaborators at other institutions in South Africa are doing computational fluid dynamics for the ATLAS upgrade. We are looking towards upgrading the ATLAS detectors to explore these physics phenomena at a larger scale, or rather, should I say, at a much smaller scale. And to do so, we have to employ our engineering skills. And where I'm particularly focused on is, again, computational fluid dynamics. What do we need to do? Well, the ATLAS detector is kept very, very cold. But one of the concerns is that there's always a chance of air leaking into the detector. Why is that bad? Once air leaks in, it brings in humidity. When that humidity comes in, that humidity will condense, and it will condense or form water onto the detectors. We do not want that because that will damage this expensive electronic components, and it will lead to failure. So what do? We are analyzing what's called the nitrogen gas flushing scheme. The nitrogen gas flushing scheme is to introduce dry nitrogen to diffuse that humidity. But there is complex physics that takes place there, fluid dynamics, heat and mass transfer, thermodynamics principles, etc. And those are pertinent to ensuring we keep the ATLAS detector dry. So myself, my team, which entails collaborators, postgraduate students, postdoctoral researchers, we build computational fluid dynamics models of the ATLAS ITK, and we build these models to analyze this gas nitrogen flushing scheme under multiple failure modes to see where it would fail and how to design the engineering systems to ensure that those specific modes will not lead to failure. And we've been doing that project for about 6 years now as we're running into the commissioning of the ATLAS ITK upgrade. And that has been phenomenal. We have proven some potential failure points. We have shown where we can improve designs. We've analyzed the improved designs and now show that those specific designs will work. So we're not only advancing humanity from a practical sort of application perspective, we're also advancing humanity's knowledge by directly contributing to the advancement of science. My research also spans greater areas than, and not greater in that they're better, but broader areas than CFD or computational fluid dynamics. Through the work that I've done with ATLAS, I've been privileged at the University of Pretoria to bring the University of Pretoria into CERN via the ATLAS experiment. And by virtue of that, I am the institutional lead or team lead for UP ATLAS. And I do that in conjunction with the Department of Physics in the Faculty of Natural and Agricultural Sciences. So I have a collaborator in that department who's the deputy team lead. And we've been collaborators for about 6 years now, even before we've joined. But since I've joined the University of Pretoria, I've been able to leverage my expertise and drive this project at a much higher level. And I continue to work in that area in employing my expertise in AI, as well as data science and quantum computing to further contribute to the science that is ATLAS. And I've also been privileged enough to visit the Large Hadron Collider, or CERN, in Geneva. This was done way back in 2019, and I look forward to going again. But my postgrads and postdocs continue to travel to and from CERN and to contribute to large-scale science on a global level. And this is a testimony to South African and African scientists and engineers. We have immense skills, and we've been afforded the privilege to show that on a global scale. So in this way, I and my collaborators and my students are leveraging and applying our skills in computational sciences, data science, AI, computer science, software engineering, mathematics or applied mathematics, physics, engineering, and we're applying this to broad-scale scientific problems, from computational fluid dynamics to high-energy physics, and also to quantum computing, as well as quantum sensing. And all of this, while they seem disparate, have immense links. Have postgraduate student who's working on not only a CFD for the Atlas ITK, but also working on designing sensors that will help monitor these specific conditions, as well as analyzing some of the data that's coming out of the Large Hadron Collider. So we're using these skills to impact science on multiple interesting and impactful fronts. And we continue to push on the frontiers of engineering and science, and we look forward to the future by making today matter.